As we just heard in the last talk, data amount and quality are key factors for safety and credibility assessment. My name is Taciak, I work with AVL, and together with Heuer and Strathmann from the DLR, I will talk about the process of field data acquisition and processing. Let's first of all go over the agenda. After we talk about the general goals and motivations, we will go over the different perspectives used to record field data, namely the vehicle and the infrastructure perspectives, how we select driving scenarios in form of locations and situations, and also how this data is used later on. Let's get the most obvious question out of the way. Why do we even need field data? Let's talk about the reasons for performing field data recordings and who the beneficiaries are. We are looking at three main groups of stakeholders. The first one is the sensor manufacturers, who seek great amounts of field data to provide statistical proof of sensor reliability, precision, and classification stability in various conditions. That, for example, means that the sensor performs as expected on a sunny day as well as a foggy or rainy night. Also, one of the upsides of using a vehicle specifically developed for performing field data acquisition is the high flexibility of being able to quickly replace or manipulate the sensor under test. Such tasks would be more time and resource consuming on a fully integrated solution like production vehicles. Also, simulation-driven development of autonomous driving functions is only possible with high-precision sensor and vehicle models. This model quality can only be achieved with high amounts of real-world data, which simulation developers can test their models against. Lastly, the ODD, or operating driving domains, are being iteratively adjusted in the function development process according to observations made in the analysis of collected field data. Thomas will tell you more about this use case at the end of our talk. After we now got the why out of the way, let's get to the how. To get the maximum out of acquired field data and avoid data incompleteness due to occlusion or similar effects, we rely on two different recording perspectives. Finn will explain the second one, the infrastructure perspective, after I tell you about the first one, the vehicle perspective. Let's start on the physical layer. Some of you may have already seen this car at one of the previous Gaia X events in Brunswick. This Audi Q5 is equipped with various precisely calibrated sensors, most of which are placed in the rooftop box we call DGT, Dynamic Ground Truth. It consists of three high-precision ground truth LiDAR sensors which generate a 360-degree measurement of the surroundings in form of a point cloud. We will see a short example of how that looks in a minute. To support this LiDAR data, the DGT is also equipped with 6 high-resolution cameras in various angles, namely 3 in the front, 1 on each side and 1 in the back. For localizing our vehicle, it also is equipped with a GNSS or GPS sensor combined with an IMU or inertia measurement unit, which at any time provides us with the centimeter-precise position of the vehicle and highly accurate speeds and accelerations of the car in every direction. On the front bumper, you can see the SUT or sensor under test, the Conti ARS 548 4D imaging radar. Using a combination of gigabit and 10 gigabit connections, the ground truth data, as well as the data from the SUT, is aggregated, pre-processed, for example undistorted, and recorded on an industrial-grade computer located in the rooftop box. Further processing like pre-labeling or anonymization is then done on our online perception hardware mounted in the trunk of the Q5. This anonymization, for example, helps us remove personal or identifying information from the camera imagery by blurring it. Let's take a quick look at our output data. In this short visualization of the LiDAR and radar data, you can see that we can easily compare the output of the radar and the LiDAR data. The small points in this image are points from the LiDAR, and the bigger colorful ones are detections output by the radar sensor. All of this data has no real value for partners or data users on the federated marketplace as long as it is in a proprietary format. Because of that, every data recorder seeking to share or sell data must implement a process for translating data in a common format, in our case, the OSI or Open Simulation Interface format. Finn will go deeper on the details of this OSI standard in his part of this talk. This is what our conversion process looks like. There are two main data sources we convert data from, our ground truth and the SUT. Our ground truth data is recorded in ROSBAGs, a recording format implemented by the open source robot operating system. From there on, our raw detections are post-processed by our internal object detection pipelines, where the ground truth object lists are generated. This is the first key part of our output. The second one is the GPS position and heading of the vehicle, which, as long as the recording went all smooth, does not need any post-processing and can be directly written back to the output format. At last, the SUT data, which already contains object lists generated by the ARS during runtime, is also converted to our target format. After the data itself is aggregated into set target format, we need to provide a little more information, like for example, the type of maneuver driven, start and end times, general regions and more. This metadata is aggregated from our raw recording and written back in form of a set description whose fields are previously defined by a common shackled file. Now, after we got the vehicle perspective sorted out, we can switch over to the infrastructure perspective, which now will be presented by Finn, who was involved with the development and operation of the digital testbed Lower Saxony.
After Daniel introduced you to the vehicle perspective and acquired data from the system under test, as well as the ego vehicle, I will now go into the details of how we enrich the data from a second perspective, the infrastructure perspective. Finally, I will present you the scenario selection part for our test drives. So, in this project, we performed several test drives on different test locations. One of these test locations is the testbed Lower Saxony, which is a research infrastructure by the DLR. This testbed is located near Brunswick on a public motorway, here A39, and is equipped with a camera-based object detection system. This object detection system is on a length of approximately 7.4 kilometers and detects and stores the information about passing objects throughout this area. This information is, for example, the position, the velocity, acceleration, or classification of the object. This information is stored digitally in a database, and we finally acquire a trajectory of a passed object. Using this data, we can now enhance the perspective of the vehicle by also acquiring information about objects not directly in line of sight of the ego vehicle. Now, after also collecting information from this infrastructure perspective, we now need to align this data with the other data. Daniel already introduced you to the ego vehicle perspective and its according data. I recently presented you the object detection data, and we additionally capture also weather information in order to get a more robust information that we can replicate the situations and scenario more realistically. These data sources have all different recording types, and these are, for the object detection data, SQL database information, and for the ego vehicle data, it's already converted into the common data format ASM Open Simulation Interface. And the weather station information is recorded also in the ROSBAG file format Daniel already introduced you to by the robot operating system. In order to align this data, we need to post-process it and convert it. We start this offline post-processing by first match the object detection data and ego vehicle data against each other. We do this by a time-based matching, so look at the time and the objects and match these against each other, and then we merge the data set. After we merge the data set, we processed. We post-process the information by, for example, applying filter and selecting the relevant time frames out of the data frames. After we now post-process the data, we convert this data, this object list, into the Open Simulation Interface file format. Also with some meta information which describes the data recorded. Additionally, we export this information as ASAM Open Scenario, which is a file format in order to describe scenarios which can be directly fed into simulators in order to replicate the scenario. Therefore, we also generate some metadata. Finally, we convert the weather station information also into the both file formats, the ASAM Open Simulation Interface and ASAM Open Scenario format. Now we have a tool chain in order to collect the data and post-process it in order to have a common and aligned data for our use cases. But in order to know which use cases we want to perform and which data is relevant, we first have to get a look inside our motivation. So our project is about the product lifecycle of an automated lane keeping system, which is an autonomous driving function defined and governed by the UN regulation 157. This regulation specifies requirements and also information about test strategies for this automated lane keeping system. To get a brief understanding of this automated driving function, the operational design domain, so the conditions which this system is intended to use, is the highway. It's a highway scenario and with a maximum speed lower than 60 kilometers. This was since what is released in 2021. And since 2023, it's also allowed to be less than 130 kilometers per hour. So the specification defines the requirements on the system and also for the testing. In the specification, in this test part for the specification, also relevant scenarios are defined. One is a cut-in scenario where a challenging vehicle will cut into the current lane of the ego vehicle and the ego vehicle needs to adapt its behavior. The second scenario is a cut-out scenario where the challenging vehicle will move out of the current lane of the ego vehicle and an object in front of the challenging vehicle will require the ego vehicle to adapt its behavior. The last scenario is a deceleration scenario, whereas a challenging vehicle slows down and the ego vehicle also has to slow down. Thus, our test drives should focus on these three scenarios since we observe this test specification, or we use this test specification for our purposes. Daniel already showed you some videos of the ego vehicle data and the perspective of their sensors. So I will now show you a short clip of one cut-in scenario recorded from this infrastructure perspective. And here you can see two camera perspectives from the testbed Lower Saxony. These are from two different sides. One is facing towards south, this is on the left side, and one is facing towards north, this is on the right side. The challenging vehicle will be marked in blue and the ego vehicle will be marked in red. So if I now play the video, the ego vehicle needs to adapt its behavior because the challenging vehicle will cut into the current lane of the ego vehicle. We can see now on the left video, there's a truck, and just behind this truck, there's this ego vehicle, and now it performs the cut-in maneuver and the ego vehicle needs to decelerate. This is just a short clip of the scenario, but the information will be stored throughout the whole length of this motorway, or the object detection on this motorway. Now, after we finally collect this data from vehicle and infrastructure perspective, my colleague Thomas will introduce you to one of the following of the possible use cases.
After you've seen how field data is gathered and processed, I would like to show you an example of using field data to close the loop in a continuous life cycle for highly automated driving functions. Let us now look at another example of using field data to support a continuous life cycle by monitoring the ODD description that is deployed with a driving function. Before extracting useful information from the data that was gathered using sensors in the vehicle and infrastructure in a test bed, it first needs to be pre-processed by removing noise or interpolating missing data, for instance. Subsequently, observables used in constraints of the ODD description like traffic flow or weather conditions are extracted from this pre-processed data. The information gathered by this is fed into a monitor that decides whether a given property of the ODD is satisfied. Based on this verdict, the ODD provider takes a decision on whether to modify and also how to modify the ODD description. If the information is positive, then the ODD description is modified, that is, an update to the description is developed. It is then validated using data or simulation techniques, and then it is deployed, finally closing the loop, so we have a continuous life cycle in this regard. Thus far, we have implemented the first part of the cycle using data from testbed Lower Saxony and constraints on the traffic flow from the initial ODD description. On the top right-hand side of the slide, you see an excerpt mentioning different parameters related to traffic flow. In order to monitor this property, we derive observables from the data gathered at the motorway segment in the testbed Lower Saxony. The observable in this case is space mean speed, which is just the harmonic mean of the instantaneous velocities of all vehicles in this segment. This is a good measure of traffic flow, and this is then compared with the ranges mentioned in the ODD description. And this then gives us a verdict that allows to judge the validity of the ODD description given this real-world data. Let's now recap and give a brief outlook on the activities during the second half of the project runtime. You've seen that data from driving scenarios was collected in different campaigns at testbed Lower Saxony, like we showed you in this presentation, but also in the invited loop and at an intersection in Grafing. You've seen one application in this presentation, which was ODD monitoring and update of the ODD description, but you will see further applications like data-driven sensor model validations in upcoming presentations and throughout the day. Right now, the activities are focused on processing and analyzing the data to enable these applications. In the second half of the project, the monitoring will be extended to observing also non-functional properties like timing of the driving function and to scenario monitoring proper using formal specifications of driving scenarios derived from the UN 157. And the activities surrounding data-driven sensor model validation will continue. Last but certainly not least, the data flows that were hinted at in the presentations will be implemented, at least in part, using prototypical Gaia-X services that are being developed in this project and outside of this project. Thank you very much for your attentions, and if you have any questions, don't hesitate to ask.